Good afternoon, everyone. Thank you for joining us. And since we have the lovely weather today, we're going to do the online version. All right. And please keep yourself muted during the process what to do. And we will also record a lecture in case you want to watch it. And now, since we're online version, it's going to be short and sweet because I will see you guys next Monday anyway. All right. So while we're waiting for folks to join us, quick things. Today, we're mainly going to do a review session. Okay, I had some students asking quite a bit, a lot of information flowing, and we need to help us sort it out, which is which. So that's one thing we'll be doing today. Quick review in terms of concept, what we have learned so far, and keep you organized. Okay, so that's the first thing. Second thing is that we are going to take a quick look at the past exam. Yes, you heard it right. From last semester, fresh out of the oven, from the first exam we had in last semester, I want to give you a feeling of what you'll be dealing with for the first exam. And we're going through some of the problems just in general. And meanwhile, I will allow you guys to work on it for about a week or two, and we can also talk about it again next week. All right, so that's all I have on my agenda. Any questions, problems, issues? So far, anything, folks? Anything? Okay, if not, I will be finishing grading later today, and you'll see your grades online, I promise you. And then also for the, well, if not latest Friday, I'm in the process of uploading it. But second thing is about the special assignment competition yesterday. I haven't uploaded the assignment yet, which I will. So details there. So all you have to do is just submit your team members and some of the results like points and then we'll update the grade on that. Okay. All right. So let's get started. Okay. So what did we learn so far? Well, again, right, Bob, you're going to repeat yourself. Concrete is good for compression. Steel is good for tension. What else? Right. So that's what we have learned. But specifically, and I want you to take a look at the grand scheme of things. And let me share my screen real quick. And give me 1 second here. All right, so grand scheme of things, we are going to talk about what we have learned today, past in terms of a organized format, right? So let's create review of flexure members, okay, flexure members. And specifically, we're talking about beams. That's right, you heard it right. So among all the stuff we have learned, we can summarize into 4 columns, right? 4 sections. You can see that. First is, I say, analysis.
No, I'm in a Zoom.
Hello? Drew, you saying something?
Oh, sorry, I did not know that I was not muted.
Oh, don't worry.
I'm going to mute myself now.
No worry, thank you. And now, the first thing is analysis of singly reinforced section. Singly reinforced section. That means that I have a section and I only have tensile reinforcement at the bottom here, and I call it AS. Okay, we call it AS. And then the next sector, we talk about analysis of AA reinforced section. Okay, that means I have a beautiful rectangular section again, and I am going to analyze the moment capacity of it in terms of both tensile and compressive reinforcement. Okay, and apart from that, what we also learn is, I'm sorry, anybody? I will have to mute you, Jay. Okay, great. So the third one we're talking about is design of singly reinforced section. Okay, now this it with section geometries. Okay, this is with given section geometry. Okay, so that is to simplify it as use red color. Is that what is my AS? Okay, so given B and given H. Okay, so B is given, H is given, and F prime C is given, and Fy yield strength is given, what would be my reinforcement needed for the singly reinforced section. All right. And last but not least, what we have learned yesterday is called design of singly reinforced section without giving or without given geometry. All right. So that means I have a section and I have reinforcement in it. Say yes right here. Okay, the intention, right? And I have here and H over here. And usually I don't know B, I don't know H, and I don't know the reinforcement area neither. Okay. So these four are what we have learned so far. Okay. So what about the logic, right? What about logic behind them, right? So I'm going to first give you some of the steps you needed. Steps you needed for all these four, okay, for all these four. So I'm just gonna do a division line, okay? And on top, I would say these are the problems. Okay, these are 4 problems that we learned so far. Okay, and we're going to talk about solutions, right? Solutions for them correspondingly as well. Right. So for the first problem, it's analysis. Where do we start? So for analysis, we start from compression from the concrete equal to tension. So I'm just going to put equation down here, okay? I'm going to put equation down here. And we know that the compression CC equal to 0.85 F prime C, A, B, and A is the effective compressive zone that is equal to beta 1 C, okay? And we also know that the tension T equal to AS Fy, and the bending moment Mn should equal to AS Fy multiplied by the distance, which is ds minus half A. Okay, so these are the solutions or equations you needed, right? So just bracket inside, this is the equations you needed to solve the analysis problem. Okay, but better yet, let's take a look at the steps involved to solve the problem, right? So to solve analysis problem, right? First thing first, you need to do the internal strain diagrams, right? So internal strain diagram look like this. First of all, I have a section here. Just gonna do a cartoonish thing, okay? And the strain diagram looks like this. This is epsilon Cu, and this is epsilon S. And if I have, say, 2 layers, I will have epsilon T, that is at the bottom here. So that is epsilon T. But usually you have 1 layer, okay? And that is epsilon T at the bottom here. So that is the strain diagram. And the stress diagram, so let me do strain. Okay, and zoom in here for you to see it clearly. So this is section, strain, and the stress, we follow the Whitney stress block. So if this is the actual compressive zone size C, this is A. So A is a little bit smaller, and then that is the compressive stress. It has a Whitney stress block of 0.85 F prime C. Okay, and the tension force is at level S right here, and that is T equal to ASFY. So this is called internal stresses. Now, in terms of forces, internal forces, that is, I'm looking at the total compression force of CC right here at half distance A away from the top, and the tension force T here. And the distance between is called JD equal to DS minus half A. All right, so that's about the diagram you need to remember. So steps. Now, first steps, step number 1, you need to do is determine the effective compressive zone size A. Okay, so the first step is determine A. That is A equal to AS Fy. Remember the tension divided by 0.85 F prime C B, which is the width of the section, right? And once you have A, you calculate your A, and then you can do a C, which is the actual compressive zone size equal to A divided by beta 1. Okay, and for KSI concrete, beta 1 is 0.85. For AKSI is 0.65. So beta 1 has this nice equation that follows this chart right here. So I'm going to label it, say now for beta 1 equal to 0.85, my concrete strength is about 4 KSI, right? So this is F prime C on the horizontal axis. Now, if you go higher than 8 KSI, right? 8 KSI is a high strength concrete, and then you end up with 0.65 as beta 1. And in between, you just do linear interpolation, right? So now once you find A and C, right? Let me just do that together. Step 1, find A and C. Then you can find the step 2, which is strain in the rebar, strain in the steel. And that is to make sure epsilon S, be careful folks, epsilon S has to be greater than or equal to yield strain of epsilon Y here. Yield strain of epsilon Y here. So how do you do that? Well, you look at the strain diagram, right? You look at the strain diagram. This is epsilon CU. Mind you that is 0.003. And this is epsilon S. Don't know that, but you have the C and you have the DS. So all you have to do is use the trigonometry equation epsilon S equal to bracket inside D minus C over C multiply epsilon CU to get your strain in the steel. And this is the S strain, not the Y, sorry, not the T, okay? And to make sure that epsilon S is greater than or equal to epsilon Y. And how do you determine epsilon Y, which is yield strain of the bars? You use the grade 60 yield strength divided by Young's modulus of steel, right? And for a grade 60, epsilon Y should equal to 60 KSI divided by 29,000 KSI, and you end up with a yield strain about 0.00207. And folks, you know that you need to remember this for a grade 60, right? And of course, while you're at it, you need to remember the concrete crushing strain epsilon CU 0.03. And of course, you need to remember this ES value here is 29,000 KSI. All right. So that is to ensure that your reinforcement yielded. Okay, that is to ensure that your reinforcement yielded. Step 3, once you confirm that, oh good, and you can try to find your moment capacity Mn here. So how do you find Mn? Mn is equal to T, which is tension or compression CC, multiplied by the lever arm JD. So in this case is ASFY multiplied by distance DS minus half A, and you have most of the values to calculate Mn. Okay, and now you find Mn, which is pretty happy, and then you say, look, I still need to find out the stress reduction factor phi, and that is dependent on the strain in the steel. So how do I know? How do I know the strain is epsilon T equal to dt minus C over C multiplied by epsilon Cu, and that is the strain for the last or most stretched reinforcement. And now you have epsilon T, all you have to do is bring into the equation phi that equal to 0.65 plus epsilon T minus 0.002 and multiply by 250 over 3. And you will find this equation from ACI 9.3.1 and find your strength reduction factor. And to be visual, you can see that phi is an equation of epsilon T in terms of strain. If it's lower than 0.002, and you have a phi about 0.65. If it's beyond 0.005, you have a phi of 0.9. In between, you do linear interpolation, right? Linear interpolation. And just to help you out here, right? Just to help you out here. So in the terms of the stress state, right? In terms of stress state, right? So this is tension controlled limit. Okay, and this is called over reinforced. Okay, and this is under reinforced. Okay, in between transition zone. Okay, so that is how you determine phi. Now, this is just the phi, and the last step for analysis problem, step number 4. Step number 4 is that you need to make sure phi Mn is greater than or equal to mu, where mu is a factor moment that is equal to 1.2 m dead plus 1.6 m live. So once your phi m and mass light together is greater than this value, then you satisfy your stress requirement. And that, my friend, end the box for problem number 1, analysis of singularly reinforced section. Pretty long, eh? Pretty long. So that is whatever we have learned so far about problem number 1, analysis of singularly reinforced section. So it's not too bad, right? It's not too bad. Okay. Once we're done with that, we went to the doubly reinforced section. And you know, for doubly reinforced section, things are a little bit different. Things are a little bit different. So the difference is that I added compressive reinforcement on top, right? And when I do that, I actually introduce such set of parameters, and this is called ds prime, and in corresponding with ds, which is the depth of the reinforcing tension. And several things you have to remember, right? So first of all, ES, which is a steel or modulus elasticity for steel over modulus for concrete, is approximately 8 times. So when you add more reinforcement, you add a lot of compression force, right? Compression force. All right. But the real reason of adding, or real advantage, right? So you say pros or advantages, let me just say advantages, that's a better word. Advantages of adding AS prime is to increase ductility. Or you can say that increase epsilon T or epsilon S, strain in the bar. All right, so that is the main reason why we are adding compressive reinforcement in it. Okay, so with that, let's take a look at the solution. So solution for the doubly reinforced section is a little bit complicated. And to be precise, let me just bring up the diagram early. Okay, bring out the diagram early because you need to see the rationale behind it. So I have now AS at the bottom, AS prime at the top. Okay, then again, I want to zoom in here so you show it. So this is section. Okay, and the strain diagram looks like this, where you have a compressive strain at the top, which is epsilon Cu equal to 0.003, of course, and then you have epsilon S prime, which is not the tensile strain, okay? Not the tensile strain. You have the actual compressive side, see it again, and you have the tensile strain for the bottom layer, epsilon S. Okay, now you look at the stress diagram. You have the Whitney stress block again, and this is A, which is smaller than C, that is precisely beta 1C again, and you have this to be 0.85 prime C, and then you have the tensile stress of Fy, but be careful. Now, since you have the compressive stress from the concrete and also from the steel, and you have to add this stress from the steel in compression side of it. So this is called the stress diagram, okay? Now, in terms of internal forces, things a little bit different now. I have CS prime, compression force from the steel. I have CC, compression force from concrete, and I have a tension force from the steel T here. And mind you that this distance between the compression of the concrete and the tension of the steel is JD steel. That did not change because this is still half A. Okay, but the distance between, let me use a different color because it's so confusing, between CS prime and T, and this is DS minus DS prime. Okay, so that is my force diagram. Why am I doing this? Because my equations for doubly reinforced section analysis has changed. What has changed? Specifically, first, I introduced a new item, which is the compressive strain in the steel, epsilon S prime, that equal to C minus DS prime, okay, and equal to epsilon Cu over C, and that's the trigonometry equation. So epsilon S prime equal to C minus ds prime divided by C and multiply epsilon Cu, right? So that's first thing that has changed or introduced new, right? Strain and compressive reinforcement. Second thing, compression force from the concrete CC has changed to 0.85 F prime C, A, B. Well, actually, barely changes at all, right? It's the same thing as before. Now, also, I have discovered that I now have a compressive stress from the concrete Fs prime equal to ES. Remember this fellow here? Nice fellow, 29,000 KSI, right? And multiplied by the strain of the reinforcement, right? Strain of the reinforcement. This fellow right here, you just calculated out in first step, right? So that is the stress in the compressive reinforcement. And be careful when you do that, you want to make sure that this is lower than or capped at the yield strength of the bar, right? So cannot exceed this limit, capped by Fy. I mean, the maximum compressive stress you're going to see from the rebar is Fy ever, right? So that is the newly introduced fellows here. And now you have the compressive force from the steel as well, CS equal to AS prime. And be careful. Remember we said something about the hose. You remove the bars, you fill the concrete back in. So there's a 0.85 F prime C minus in the bracket behind this whole thing here, okay? And that is the compressive reinforcement. Compressive force from the compressive reinforcement, right? So I'm just gonna cheat a little bit, say Fs prime, okay? Cheat a little bit, Fs prime. And be careful about this minus 0.85 F prime C here, okay? People often forgot about this, okay? This is very important. Be careful about this 0.85 F prime C minus sign here, okay? All right, so that is the compressive force. That is the compressive force. Now, don't forget the tension, total tension force now, that is actually equal to the compression force of the concrete added to the compression force of the steel. So ASFY equal to both the concrete compression 0.85, F prime C, and A, let me just write it out in terms of C, and that is beta 1, C, B plus AS prime multiply FS prime minus 0.85 F prime C, okay? Sorry, let me just realign it so it will see it better. So this is plus AS prime, okay? Multiply AFS prime minus 0.85 and F prime C here. That is the total tension force. Right? So that is the equations, right? Or we call it solutions. Now, in terms of steps, okay? So what are the steps to find my capacity, moment capacity of a doubly reinforced section? What are the steps? That number one, first thing first, what you do. What is step number one here? Step number one is what? Is actually try C, okay? Try C, which means I estimate the C. And how do I estimate that? You start by C, any value that is arbitrary value that belongs to a quarter of ds or 1/3 of ds. Start from there, okay? You estimate it, you don't know, but you estimate it, okay? Once you estimate the C, now you're able to do the following. What is the following? The table. What is the table? Table like this. Let's just clean up on the left, give me a little bit more room here. And the table looks like this. Okay, I have first row, which is actually C, different C values I'm trying here. Different C values I'm trying here. Don't like this much. I'm just gonna reshape it. Horrible in drawing tables. Don't know, didn't learn very well my grade. But that is first row of C, and say, let's just say some number x here, right? You do one iteration. So I call this first iteration. So first iteration, right? First try. Some number here, okay? And I'm gonna mute you, Jessica, okay? If you have questions, just speak up, okay? Thank you. All right, and now second try. Second try. And don't forget, third try, right? You have to try 3 times. You have to try 3 times. You say, wow, I forgot. Why are we trying this again? Why are we doing this? I hate tables. Why are we doing table again? Because it will simplify your life as we are doing this. Epsilon S prime equal to C minus ds prime divided by C and epsilon CU. That is, you give a C, you plug in the numbers here, and you get this strain in the compressive reinforcement, and the Fs prime stress in the compressive reinforcement is simply equal to ES epsilon S prime, and that has to be smaller than Fy, don't forget. And if it's just bigger than that, you capped at it, okay? You capped at it. Okay, Bob, what do you mean by cap? Meaning you let it equal to Fy, right? You let it equal to Fy, the maximum value ever, right? And you do that. Next one is that CS, remember, compression force for the steel equal to AS prime, area of steel in compression multiplied by Fs prime minus 0.85 F prime C, okay? And then that is the total compression force. And then CC, compression from the concrete, 0.85 F prime C, A, which is beta 1, don't forget C, B, right? And then that is the compression from the concrete. Then what you do T equal to ASFY, total tension force of the bars. And what you do now tension and compression has to equal to each other. So what is my compression, right? And you do compression. Okay. And then afterwards, you say whether T equal to compression or tension, whether tension equal to total compression or not, there's a question mark here. And the error requirement is that it has to be within 1% of error, okay? Minus or plus 1% of difference, okay? So what are we doing here? You keep trying different C values, okay? You keep trying different C values until you arrive, all these numbers arrive at 1% of difference, then bingo, that's your ultimate C value here, okay? All this hassle, all this work, just to help you to determine the C value. The C value, that's just step what? That is step number 1. Wow, so involved, okay? For W reinforced section, step number 1 is this fellow right here. Okay, you find your C basically. Try a number, start by something between ds over 4 or ds over 3. You play around this table, you try 3 iterations, somewhat you arrive at the C value you're happy with, as long as there's 1% error, okay? 1% of error. And then step number 2, after you get a C here, you say, I'm going to check my strain and make sure my strain yielded. Same thing as singly reinforced, right? Singly reinforced section. So epsilon S, that equal to ds minus C over C multiply epsilon CU. And there's a equal sign I forgot here, apologize, epsilon S equal to that fellow here. And you have to make sure this one is bigger than epsilon Y, okay? And again, remind you epsilon Y for a grade 60 of rebar is 0.00207. Don't forget, don't forget. And once you have that, oh, happy faces, you say, okay, look, once I have the strain in the steel epsilon S, since I have computed all this nice little bit fellow right here, I have computed that. My last column, right? And my last column, I have computed all that. I said, look, I just have to find my moment. Find my moment. And my MN, miraculously, it's easy. And the equation changed a little bit, okay? Now it's no longer just ASFY thing, but becomes CC, compression force from concrete, multiplied distance between the concrete forces and the rebar, and plus a CS multiplied ds minus a ds prime. And now let me make it more clear so you see it better. Now there's a ds minus ds prime. Okay, sorry, I have to eat out some of the space for my third column, but that's it. Okay, step 3, that's the MN. That's the MN. Now, step 4, okay, step 4, what I'm doing here. Step 4 is I need to find my stress reduction factor phi here. What is my stress reduction factor phi here? Phi MN. So phi is the equation of epsilon T, remember? So I'm just going to say, look, I've done this. And this red fellow right here. And, you know, I'm going to drag this equation here and I'm going to use that and find my phi. And last but not least, once you have phi, step number 5, step number 5, what you do is phi MN, again, has to be greater than or equal to mu, where mu is the factored moment. Okay, so that's what we have learned for analysis of singly reinforced section and analysis for doubly reinforced section. Okay, and now one thing I mentioned briefly, but I did not say clearly in the previous lecture is that oftentimes you need to add one more thing. Okay, oftentimes you need to add one more thing. That is check. This is step number 5 here, and this is for it, step number 6 here. Okay, is to check minimum reinforcement requirement, and this, if you care to look at it, is ACI on ACI 31819 9.6.1.2. All right, and those two equations are same thing. AS min are the larger of two. What are these two? First one is 3 square root f prime c fy bwd, and the other is 200 fy bwd. And this is the same thing for doubly reinforced section. You may ask, Bob, what do you mean by same thing? Doubly, I have compressive reinforcement. You do, but when you check for AS min, this is only means tensile reinforcement only. Tensile reinforcement only. Don't have to worry about the compressive reinforcement, okay? And the same equation applies. All right, so a little bit long, but not a big problem. You know, just simply analysis, right? Analysis, okay? Analysis. And you may wonder, Bob, what do you mean analysis? Analysis meaning if I give you a section, give it a reinforcement, you need to know how to calculate it. You need to know how to calculate the moment capacity. All right, so that is so-called analysis. Okay. All right, so I'm going to pause here for a second. Any questions so far, folks? Are you still engaging or fall asleep already? Anybody? Any question? All right, good. I got 1 thumbs up. Okay, somebody's listening. All right, just one person. Okay, buy a coffee. How about that? All right, that's good. Okay, well, let's continue. Okay, I know it's going to be a little bit dry today, but I hope I can help you organize and just let you on a little bit secret, right? Once you have this PDF, you can understand it and reword it and put on your crib sheet, right? Put it in crib sheet. Okay. All right. So now we have learned analysis where big boys now, right, want to do design problem. Big boys and big girls want to do design problem, right? So there are 2 types of design. One is design of singly reinforced section with given section geometry. Meaning I tell you that I'm designing a beam with so and so width, so and so height. You tell me what is reinforcement? How many rebars I'm going to put in the section? All right, plain and simple. And for that, usually in terms of solution, okay, in terms of solution, I often give you the MN. I give you the MN, and you need to find out the AS. Okay, and to be precise, number of bars, so on and so forth, and also number 9 bars. Let's just put number of bars. Okay, sorry, bad habit. That is hard. Okay, number of bars, and also what is the minimum beam width? Again, so bad. I keep messing it up. Minimum beam width, and also bar spacing. Those are the details. Remember, bar spacing. Those are the details. Okay, I am not going to say a whole lot about the equations because you have seen those equations you need from the problem number 1 analysis. Okay, let's just go right into the steps, right? So how to solve the problem. So steps number 1, what you need. What you need first is that you need to find out how much reinforcement you have. How much reinforcement you have to estimate it. Okay, so how to estimate reinforcement? How to estimate a reinforcement? You can't, right? So you just do estimation first. So AS equal to this equation right here has to be greater than or equal to mu. Again, mu is a factor moment, usually it's given, divided by phi fy ds minus half a. But you know, for this condition, I don't really know phi, so you assume phi equal to 0.9, and you assume ds minus half a to be 0.9 ds. And now the equation becomes AS has to be greater than or equal to mu divided by 0.9 Fy, use strength of the bars, and then bracket inside, or let me just throw the bracket out, and this is 0.9, 90% of ds. 90% ds. Okay. Now, again, at this point, you may ask the question, Bob, I don't really know about ds. Well, we said about it, right? So ds will have one layer of bars equal to h minus 2.5 inch. So one layer of bars. Okay. And the other is h minus 3.5 inch when it's multi-layer, right? 2-layer or above, right? Multi-layer. Okay, that's how you estimate ds, right? You know how to do that, right? Because the height is given, section is given, so you can estimate ds. Okay, all right. So once you have as, right? Now let's just call it as estimate. So as estimate. You arrive on a certain area, right? You arrive on a certain area, right? And then you say, look, step number 2. Okay, I'm going to use as estimate to determine what? Determine A. Determine A. So how to determine A? A now should equal to what? A should equal to ASFY, and this is AS estimate. Okay, use AS estimate. So I'm just gonna do a mark here. AS estimate. Okay, multiply FY divided by 0.85 F prime C B. Okay, the width of that, right? And you get A, and then beta 1, sorry, actual compressive zone C should equal to A divided by beta 1, and that's your C. And then step number 3 is to do what? Is to recalculate. This is new, okay? Folks, pay attention. Recalculate AS. So how did we calculate AS? Now AS has to be greater than or equal to, use the same MU again, and this is 0.9 again, and this is FY, but instead of 90% DS, now you actually have an A to use. So use this nice little fellow here, and then bring into this equation and find your AS. And now with AS, you say step number 4, select bars. Okay, select the bars, and then how to select bar AS provided number of bar has to be greater than or equal to AS from the step number 3. All right, okay. At the end of step number 4, you are looking at a scenario that you have a width that is given by the problem, you have the height given by the problem, and you know the concrete cover usually is 2.5 inch or 3.5 inch, depends on the 1 layer or 2-layer, but never you mind, you now have AS as well. Say, I don't know, maybe number 9 bar, 2 number 9 bars, you name it, right? You select the bar, remember? You select the bar so you know everything. Once you know all this, and step number 5, compute MN and phi like problem number 1, right? Like the analysis problem. Basically, now you're going to use whatever we learned from problem number 1 to problem number 3, okay? Basically repeat that, right? Repeat that. All right. So once everything is said and done, now last but not least is the detailing, okay? You're doing design, right? So gotta do detailing. So what are the detailing? Detailings are here, meaning that you have to determine at the corner. Don't forget there are stirrups, remember? And you put a bar there. And this is concrete cover. And remember there are table 20, 0.1, 0.5, 0.1, 0.3, 0.1. Remember? To tell you the clear concrete cover on the side and everything, exposure, exterior exposure, interior exposure, you know, pre-casting, cast in place, whatever, right? This is on ACI, right? So there you go. You find the spacing, you find the concrete, and you know, depending on how many bars, you find a half minimum width, okay? And also you check textbook, table A5. Because there you have a standard, right? You have a standard width. But be careful, right? That standard width has nothing to do with the calculation you're performing here, because the table A5 is an ideal situation, right? Okay. And now once you have done that, remember there are, say, if you have 1 layer of bars, 2 layer of bars, spacing requirement, remember spacing requirement, this is 1 inch dB, 4/3 the aggregates, remember, has to be the maximum of that, right? Whether you have enough spacing, and all this goes into detailing calculation, right? And then you're done. Okay, you're done. So that is, my friends, design for single A reinforced section with given section geometry, meaning you know the size. You need the size, you know the size. Okay. Now, number 4. What is number 4? Oh, you know, number 4 is a little bit complicated. Remember last lecture we said something about it? Okay. And number 4, we have to do a design without any information on the section. So I'm going to say, if I'm going to do that, I need to do this. First thing, solutions. That means equations, right? You need to do analysis and equations and everything. So first thing first, we define several parameters, okay? We define several parameters. Rho equal to AS, only the tensile reinforcement, okay? Divided by BW ds. That is rho. Omega equal to rho Fy over F prime C. Wait, let me see if I did it right or wrong. I think I made a mistake here. Just give me 1 second. Rho equal to ASFY, good. And omega rho Fy over F prime C, no problem. I didn't do anything wrong. That's correct. Then don't forget rho, and for design state, epsilon T has to equal to 0.0075, which means it has to be tension control limit. Rho equal to AS over BW ds, also equal to quarter beta 1 multiply F prime C over Fy. Okay, and this only applies when the strain is at 0.0075, okay, which is bigger than 0.05. That is why it's tension controlled. Okay, and now let me name some names, right? Rho, and this is especially for exam, rho is called a reinforcement ratio. All right, fine. Omega is called a reinforcement index, but omega is only the function of F prime C. Oh, sorry. Well, yeah, sure. Let's do that. It's only a function of, actually not F prime C. It's only the function of beta 1, and then beta 1 is only the function of F prime C. Okay. So when we say reinforcement index, it's really just concrete. It's really just concrete. All right. Okay. But this is not over, right? This is not over yet. And we have talked about this last lecture, right? Just like last lecture, right? So what we have learned last lecture, we said, after I know this, I have reinforcement index, right? I come up with another fellow here. It's called what? R, defined as omega F prime C, bracket inside 1 minus 0.59 omega. And this R fellow here is called, it's called flexure resistance factor. Flexure resistance factor. With that, I say, look, Mn is just equal to R B D S squared. So if assume alpha equal to B over ds, then I know that B ds squared has to be greater than or equal to mu over phi r, or alpha, or to be precise, not alpha, ds has to be greater than or equal to mu over phi r alpha to the power of 1/3. And now you determine ds and h, height approximately equal to ds plus 2.5 for one row, ds plus 3.5 for multiple rows, inches, you get a height, and usually b equal to alpha multiply ds, and you get the width as well. So now you have a section that is given width and depth is also estimated. All right. But usually B is given, okay? Usually in design, I tell you B, just have to determine H or height, okay? Once you arrive at this step, you say, look, now I have finished everything on the section. This problem just become problem number 3. That is design for a known section geometry. Let's just repeat the problem number 3 now, right? So that is everything we learned so far. And I can manage barely to fit in 1 page. That's it. And if you want, this should be your crib sheet. If you want, this should be your crib sheet. Okay. All right, it's not too bad, eh? Questions? Anything, folks? Anything?
Could you show the bottom of the bottom 2 or last 2 columns for steps 3 and 4, please? Or problems 3 and 4?
Problem 3 and 4. Yeah. Do you see it?
Yeah, thank you.
No problem. Okay, so that's everything, folks. That's everything. So I just created a crib sheet for you. I just created a crib sheet for you. Feel free to add anything to it, or try to understand it, try to memorize it, try to put it on your whiteboard, and before you sleep, you look at it, understand it. Of course, you don't do that, but try to do that, right? I used to do that. All right. So logical sequence, you can see that 1 to 3. You need a 1 to do 3. And also you need a 3 to do 4, right? So that's a logical sequence. So 2 is kind of like a loner. 2 is kind of like a loner, right? So it's analysis of doubly reinforced, but we will not ask you to do design for a doubly reinforced section, at least not from this lecture, from this course. All right. So why am I showing all this? Because now you see you have 4 problems, and you are expected to solve these 4 problems in the exam number 1. In the exam number 1. Cool, eh? All right, so that's the deal. That's the deal. Okay. All right, now I'm going to stop sharing. Of course, I'll upload these notes to Canvas, which you have it. And this will be recorded as well. So feel free to watch it again if you want. And it's pretty dry today, but I understand. But I think it's necessary to clarify the content so far. Okay. All right, I'm just going to stop sharing for now. And let me show you what you will be dealing with in terms of exam number 1. And by the way, I just uploaded this document to Canvas as well. See how generous we are, eh? All right. Can you guys see it? Can you give me a thumbs up if you see this? Any reaction so I know you're seeing it? Good.
You can see it.
Yeah, good.
Yeah, I see it.
All right, wonderful. All right, so as I said, unfortunately, today is more like one-way output, information explosion today, I understand, but I just want you to have a sneak peek of what you will be challenged by, right? So this is first exam I made, 2021, February, okay? And for the exam, you see that, write your name on the space, provided on each sheet here, and you can use letter size, crib sheet, front and back, both sides of it. 31819 code, you can bring it, calculator, you can bring it, but that's it. And when you're done with the exam, I need everything. I need a white sheet, whatever you use for filling up the exams. And I also need them to be stapled and submitted to me, okay? All right, so first thing first, problem number 1, short answers, okay? A value of beta 1 equal to 0.7 correspond to specified concrete compressive strength of what? Okay, so this means it has to be linearly interpolated, right? So check out equations and find out the values, okay? Check out equation, find out the values. Which the following statement is correct. Unit weight of reinforced steel, unit weight of reinforced concrete is larger than unit weight of steel. Unit weight of reinforced concrete is same as unit weight steel. Reinforced concrete is smaller than unit weight steel. The unit weight of reinforced concrete is also small, that is negligible. Well, which one? Right, so which one is heavier, steel or the concrete? Steel is heavier, okay? Regardless your impression, steel is actually heavier, okay? Steel is heavier, so you know what to do, right? Compressive strength concrete normally evaluated by the testing cylinders that 7 days, 14 days, 28 days, or a year, 365 days, which one? Well, definitely not 7 days, right? We'll test that, but that's early day strength. Now 14, and still too early. Not 365, just too old, right? Too old, that's for backup, right? So which one is the correct answer? You know it. Now, which of the following statements is correct? The tensile strength of concrete is equal to the compressive strength of concrete. No, I don't know. I don't think so, right? It's not symmetric. The tensile strength of concrete is approximately 33 of the compressive strength of concrete. 33%, that seems to be high, okay? Tensile strength of concrete, approximately 10% the compressive strength of concrete. Let me think, how do I do that? 7.5 square root of F prime C comparing to F prime C. Yeah, I would say 10% sounds like it, but I'm not sure. Look at the last one. Tensile strength is only 1%. The compressive strength is too low, right? So which one is correct? Which one is correct? All right, so 1E, given reinforced concrete beam with strain and extreme tension layer, So for a beam, the top in compression, bottom in tension, that means it is the lowest layer, the last layer, or the most stretched layer, right? And to say that extreme tension layer reinforcement epsilon T, be careful, not S, not Cu, but epsilon T, that is equal to 0.03 at a nominal flexion strength reduction factor, phi, that equal to 0.9, 0.825, 0.733, 0.65. You use the equation, you plug in, you find out the values. For all values at prime C, the equivalent rectangular stress block has a height of 0.85 times the neutral axis depth, so blah, 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 blah. This is too easy, right? You can take a look at the block and determine which one is correct, okay? Now 1G for precast concrete beam that is not exposed to weather or in contact with ground. What is the minimum concrete cover specified ACI 31819 code? Must be provided for number 3 reinforcement bars at the stirrups. What is asking? What's asking? This is asking for concrete cover. Which one you need to look up for? The table 20.5, 0.1, 0.3, 0.1, right? Something like that, right? Remember, go back to your notes, take a look at your code, find that table, and the table is concrete cover for non-pre-stressed members. Non-pre-stressed members. All right, 1H. Beam A, beam B shown have identical dimension, mean the width the same, height the same for both sections, and material properties, both of curbside concrete and prime C. Which of the following is true with respect to nominal flexure capacity for positive bending? Be careful. Positive bending, meaning the top is in compression, the bottoms are in tension, right? Positive bending, okay? Now, which one has higher moment? Well, what is the moment? Mn equal to T, which is ASFY, multiplied ds minus half A. So whichever has the largest ds minus half A has the largest lever R, that is distance between the compression to the centroid of the bars, have the largest moment. So which one has a deeper depths? So you look at the reinforcement arrangement. I have smaller bars on the top, bigger bars on the top, compared A and B, right? So which one has the lowest center in terms of the centroid of the group of bars? Answer is A. A has the lowest center of the group of bars, right? That means I have a highest distance between the compression and the tension. So which one has a larger moment? Think about it. Think about it. Okay. All right. Consider the cross section shown below. The beam is in positive bending again. Positive bending again. Material strength F prime C 5,000 psi. Yield strength grade 60. Concrete normal weight. Maximum aggregate size 3/4. Bottom bars are arranged in 2 layers. The clear cover all sides 2 inches. The clear cover from all sides 2 inches. Okay. Save you from computing from the table. Okay. You need to find out what is cracking moment. How to calculate cracking moment. You should know that by notes. The D, and I didn't write anything here, meaning D is ds. If I don't write anything, D is ds. dt is just the last layer of bars, right? You need to find the center of the bars and also find the last layer of bars. And B mean, minimum beam width. So 2 ways of calculating it. One's go through detail, add out from the side and multiply by 2, and then compare with table A5. Table A5. Can you do table A5? I don't know. Clear cover is 2 inches. I don't know if you can do table A5. All right. So better do it by hand and then compare with table A5. Okay. All right, so problem number 1 is done. Problem number 2, analysis. Analysis, meaning no design, everything's given. And look at the cross section. Should I say this is singly reinforced, doubly reinforced? Well, I have compressive reinforcement. It must be doubly reinforced. So this is analysis of doubly reinforced. It is problem number 2, and identically to the problem number 2 I just show on the notes. Okay, so now with this doubly reinforced section analysis problem, what is my MN? How to compute MN, you should know it. Draw the strain distribution. Strain distribution, label the key value strain. What are the key values? Epsilon Cu, epsilon S, epsilon T, and C, the actual compressive zone size, and depths of neutral axis that is C, right? And then the depths of reinforcement of the section, right? What is depth? Label here, right? Labeled here. So all that. To C, verify whether the area reinforcement provided meets the minimum requirement AS min, that is checking AS min, the 2 equations, 3 square root f prime C over Fy, 200 over Fy, both multiplied by BW ds, whichever is bigger, give you that AS minimum. So check that. Last one. If the beam is subjected to uniformly distributed surface load, omega DL, dead load, what is the factor? 1.2. And the concentrated surface live load, factor 1.6, shown above, right here, right? I have a distributed dead load. I need to calculate the moment in the middle span, multiply at 1.2 a factor, and plus a concentrated live load cause the moment in the middle span, multiply by a factor of 1.6. That will be the total MU, right? And you have the MU, and you know the moment capacity of the section, determine whether the beam is adequate to resist applied load in fracture. So what are we doing here? Vmn bigger than or equal or small than mu. Determine that. Last problem. Cast in place concrete pole and pulling from the top, pushing at the top, I'm sorry. And then I have a moment of Mmax equal to PUL, right? You know it's 350 kip-foot. Save you the trouble. You don't have to compute. It's already 350 kip-foot, okay? Ask you, where is the maximum bending moment? The top and the bottom? Of course, it is in the bottom here, okay? Now, pay attention. If the force is pushing the top like this, right? So the bottom here, left side of it is seeing tension, right side is seeing compression. If you don't understand that, go back, review your mechanics materials, okay? So if the beam is pushing in this direction at the end of it, the left side of it on my left, you're facing the paper, on your left is in terms of tension, on the right in terms of compression, okay? So reinforcement wise, the reinforcement should be on the left side of it. And if I draw the section here, the bars should be here on the left side of it, close to the PU, okay? The bar should be here, okay? The bar should be here. I'll say it again, the bar should be here, okay? Be careful, all right? So this is what? Asking you to determine, assume F prime C4 KSI, yield strength 75 KSI, okay? Be careful, yield strength changes from grade 60 to 75. Maximum aggregate size 3/4, shear reinforcement consists number 3 stirrups, the pole is inside, blah, 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 inside of the enclosed stadium, or it will not be exposed to weather. It means you have to find the concrete cover according to interior exposure. Now, if the width B is restricted to 10 inches, look, I helped you, right? I told you it's 10 inches of B, right? Don't do anything else. Let B equal to 10. Don't do 9, don't do 8, just do B equal to 10. Design the rectangular concrete pole, the section where the maximum factor of moment is acting. The section should be singly reinforced, tension controlled. What is singly reinforced? One, well, few layer, but maybe fine. On one side, only the tensile reinforcement is provided. And tension control means strain of the bar has to be bigger than 0.005 with a single layer, very specific, okay? Single layer. And only 8, 9, or 10 bars, number 8, number 9, number 10 bars are to be used. So pick one, okay? Assume the central reinforcement to be 2.5 inch from the stream tension face of the cross section. That means the concrete cover on the tension side is 2.5 inch from the side to the centroid of the bars. Determined, I told you already. Just check VMN, okay? Check VMN and compare that with the factored 350 kip-foot of moment. All right, and last but not least, once you finish design, draw your design on the section. Remember which side is tension? Left side. It's intention. So the bars better be on the left side. If I see the bars on the right side, no points, no points. And label dimensions, meaning I need the details, bar spacing, concrete cover, where are the stirrups located, where are the corner, show me, show me. All right, that's it. That's everything. Okay, so what we're gonna do? What we're gonna do is that you're exhausted right now, and you don't remember a single thing that I said just now because I went very fast and you haven't reviewed yet. So the best thing to move forward is to go back, watch the recorded video again, go over the notes I did today, and then start practicing exam number 1 that is uploaded. Bring me the question next Monday, and we'll talk about it next Monday and Wednesday. All right. Well, with that, I thank you, everybody. I'll leave the homework today as well. You have 1 week again to submit it, and I see you on Monday. All right. And feel free to left behind and stay behind and ask me any questions you have. Okay. Thank you, everyone. Bye now.
Thank you.